Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about the properties of exponents. All right, let's get started. We got a bunch of properties to go through. So properties these are the rules that we use when we're dealing with exponents and values. So the first is the product of the powers. Product of the powers says that a to the m times a to the n is equal to a to the m plus n. So what is required in this case is that we have the same base, right? So a is our common base. An example would be times 3 squared is going to be equal to 3 to the 5th. So let me just change this here because this part is incorrect. So we have 3 squared times 3 to the 3rd is equal to 3 to the 5th. All right, so you have some same base to some different exponent times some same base to some exponent equals that same base 3 to the 2 plus 3, so 3 to the 5th. And then you have to evaluate it from there. Okay, power of a powers says that if I have, so product of powers, so here I have product a times a to the n is equal to 3 to the 5th, or a to the m plus n. Power of a powers, we're taking the power of a power. So n, power of a to the m to the n. So power of a power. And when we do that, we're going to, instead of adding, now when we're multiplying the two same bases together, we're going to take that one base, and now we're going to multiply the two exponents together. So it's a to the m times n. So an example would be 3 squared to the 3rd would be 3 to the 2 times 3, or 3 to the 6th. Power of a product, now we don't have the same base, but we have the same exponent. So in the first case, product of the powers, we had the same base. Let's just say same base. And in the power of a product, we have the same exponent. And in this case, what we can do is we can multiply a and b together and take them both to the m. So the exponent stays the same, but we multiply a and b together. And notice here that the base stays the same, right? I have a to the m times a to the n is equal to a, the same base, m plus n. In this case, I have the same exponent. The exponent stays the same, but I multiply the two bases together. So I have 3 squared plus 4 squared is the same as 12 squared. And let's see if, and it should be again multiplied by. So let's change this again, getting the pluses and the x's mixed up. Okay, so we have 3 squared, which is 9, times 4 squared, which is 16. 9 times 16 is 144, and 12 squared is also 144. So if we do the math, we see that this particular equation, it holds true. Now, negative exponent, this is where most of the students get caught up, because they're thinking that a negative exponent means some negative value. But in fact, what it just means is the reciprocal of whatever value you're given. So if I have a to the negative m, that means 1 over a to the m. If I have 1 over a to the negative m, that just means a to the m. So for example, if I have 3 to the negative 2, that's 1 over 3 squared. And if I have 1 over 3 to the negative 2, the reciprocal of that is just 3 squared. So it just says take the reciprocal. It doesn't mean apply a negative sign. Then the next is the zero exponent property. And that just says that anything to the 0 is going to be equal to 1. Okay, so you're going to use these properties of exponents to simplify expressions that you're given when you're given equations, or you're required to simplify some particular expression. All right, moving on, we have a couple more to go. And we have quotient of the powers. And here we have the same base, a to the m divided by a to the n. And now we have a to the m minus n, whereas when we had the product of the powers, right, product of the powers, we were adding. When we have the quotient of powers, we're subtracting the exponents. Again, same base, different exponents, now we're subtracting. Power of a quotient says that if I have a to the m divided by b to the n, and we take that all to the z, that's going to be a to the m times z divided by b to the n times z. So an example would be An example would be 3 squared divided by 2 to the 4th. I'm taking that all to the 3rd. That would be the same as 3 to the 2 times 3, or 3 to the 6th, divided by 2 to the 4 times 3, which is 2 to the 12th. So again, we're using these to simplify expressions. Okay, so let's go through some examples. If I have w to the 5th times w to the negative 8th times w to the 6th, I'm going to use a product of the powers. So let's go back to our properties. And you want to keep these handy. That's why we're taking notes. We're going to go to the product of the powers. It says the same base to some power times the same base to some power is equal to that base to the power of the m plus n, or the two powers added together. So in this case, we have w to the 5th, w to the negative 8th, w to the 6th. We're going to add 5, negative 8, and 6 together. And we end up with w to the 3rd. So we're using the product of the powers to simplify w to the 5th times w to the negative 8th times w to the 6th. We end up with w to the 3rd. The second example, we have c over d to the 4th. c over d to the 4th, and we're taking that all to the negative 2. Okay, so remember, when we take it to a negative value, we're not applying a negative sign to the expression. We're just taking the reciprocal of each of the values. So in this case, I'm going to handle these independently. I have now c, and I'm going to use the power of a quotient, right? So we go back and let's take a look at the power of the quotient. Power of a quotient says that a to the m divided by b to the n to the z, the same as a to the m times z divided by b to the n times z. So I go back to my example. I use the power of a quotient. Now I have c to the negative 2 divided by d to the 4th times negative 2, and end up with c to the negative 2 divided by d to the negative 8. And that is just the same as 1 over c squared times d to the 8th over 1. So remember, we take the reciprocal of each value. That's what the negative sign says. So we use the property of the negative exponent, and we do exactly what I did here in this example. Now I have d to the 8th over c squared. And finally, let's talk about scientific notation. Scientific notation is just a means for us to express very large numbers in a very simple format, or very small numbers. And what we're going to do is we're going to simplify 85,000 in scientific notation so that the n value, in a form n times 10 to the x, where the n value is always going to be between 1 and 10. All right? And then we provide a value of 10 to the some value exponent in order to correctly state 85,000. Well, I know that 10 to the 4th is the same as 10 times 10 times 10 times 10. And each time I'm just really adding a 0 to the 1. So I start with 1 0, 2 zeros, 3 zeros, now 4 zeros. So 10 to the 4th means I'm going to end up with 1, 2, 3, 4 zeros. Okay. So now I have 8.5 times 10,000, and that's the same as 85,000. How I generally work these problems is I take the value, let's say it's 373,000, and I start with the decimal point here. We know it's 0, 0. And I figure out how many times I need to move this decimal point each unit in order to get to a value that's between 1 and 10. So you can see I've moved it 1, 2, 3, 4, 5 times. Now I have 3.73 times 10 to that value, or the number of times I've moved the decimal place. Okay? In the same fashion, we can work on or create very small numbers and convert them to scientific notation. In this case, I'm moving in the other direction. Before I moved from right to left, the exponent's going to be positive. Now I move from left to right, the exponent's going to be negative. So here's 1, 2, 3, 4, 5, 6. So here's my decimal point. 7.27 is between 1 and 10. So now I have 7.27 times 10 to the negative 6. So 1, 2, 3, 4, 5, 6 decimal places. From left to right, it's negative. From right to left, from left to right, it's negative. From right to left is going to be positive. So I end up with 7.27 times 10 to the negative 6. And that's how you treat scientific notation.